Uh, Good morning, everyone. Today is August 8th, 2020, and welcome to the Pandemic Science Chat. I hope you guys have all been finding something for yourself to do during the pandemic. Today, we have with us Roger, James Keene, Bill Lucas, Alistair, Ian, and Carl. So welcome, everyone. Quite the group today. Everyone's on time, right early on the hour, so thank you for that. So this is an open science chat. So just wondering if you guys got any topics which are top of your mind. If they're not, then I was going to do a little thing I call the mailbag, because there's quite a few mail messages I haven't been able to respond to. Maybe you guys would be interested in seeing what's going on there. So how are things going on the other side of the pond, Ian?
Well, I was going to say it's going so badly, but unfortunately we had a sort of a second spike of this thing that you referred to a moment ago. This is a general thing around the world. So 3 of the counties of Ireland have actually been closed down, a second closed down. This has just happened in the last 24 hours. It doesn't include my own area, Dublin, which is the capital. But apart from that, things are nice. The weather is beautiful. It's tropical for this part of the world. I'm dressed in short sleeves, which is unusual. It has to be above 23 degrees before I go down to short sleeves.
Yeah, it's nice. It's summertime here in the United States. If you look at the COVID map, it's like the United States is like completely red. Well, if you've ever seen that map, and here it's like we haven't even finished the first wave. I mean, really, the statistics, it's like it went up, it kind of leveled out, and now that we're reopening, it's going right back up. So it's like all the severe lockdown here in the United States resulted in nothing but maybe leveling out the cases, maybe. It really didn't have any effect in actually reducing it is the problem, I think. Right? It's like we would have been happy to keep on doing that, except it just doesn't seem to be stopping it, right? It just doesn't contain it.
I think the problem probably is that all it's doing is slowing the case rate. Doesn't mean that the same number of people throughout the world are going to ultimately get it, and the same number of people, therefore, are ultimately going to pass away from it. It's kind of like taking a cat and clipping its tail at one knuckle at a time instead of just doing it all at once. And the only reason I can see that they've done what they've done with the lockdowns is possibly to keep the hospital system from being overrun, overloaded, because no matter how many times they do this, until you get herd immunity, which means roughly 85% of the population has had it and recovered or passed away from it, it's basically going to be with us. So all they're doing is extending the time without really much effect on the death rate in the end. Yes, it won't happen all at once, but I think the death rate will be the same either way. If they hadn't done this at all and just kept the economy open, if they had just protected the elderly, the ones that are most vulnerable to it, and those that have pre-existing conditions, if we sequestered those until everybody else, so like it ran through the rest of the population, because most everybody else recovers. And in fact, I have a friend that I communicate with through letters, old style letters, that's in prison, and he told me that 85% of the prison population has already had it. Only 3 people in his entire prison died from it.
I tend to agree with much of that, by the way. Who's speaking, though? I didn't gather.
This was Carl.
Oh, it's Carl. Okay. I agree with probably most of what you say. And I'm a bit optimistic in this sense that looking at what happened with the Spanish flu, 1918 to 19. A similar experience, and then they had a sort of a second wave, and then even a third wave, and then suddenly, of its own accord, it went away completely, probably because this herd immunity had actually kicked in. So they've probably prolonged the agony, actually, and they've maybe mitigated the incidence of demand on the hospital services, and also being a little more cynical, they have just acceded maybe to political pressures that it appears they were doing something. So in the long run, I think it's going to have to take its own course one way or the other.
Well, I certainly think that making it so that the hospitals aren't overwhelmed is certainly an important thing. I mean, as bad that it is here in the United States, we haven't had to do what China did, which is to build a 2,000 bed hospital in 2 weeks, or convert all the places that we converted into emergency beds, like convention centers. So we turned out to not really need them. And I'm not exactly sure what the situation on the ventilators is, but people are saying anyone who needed a ventilator got one, I suppose. Although it would seem that if you're going on a ventilator, you're pretty much dead anyway. So there's some talk that intubation is just not an effective course for COVID. So it may turn out that those ventilators weren't going to help anyways. But I myself, when my mom passed away, I mean, I actually entered the COVID ward because they have to basically, until they figure out whether you have it or not, they have to assume that you do. And, I was in the emergency ward, and everything there was calm and quiet, and people seemed to have things well underhand. And even in the COVID ward, it's there weren't people in the hallways and stuff like that. It was clearly not at capacity. I mean, there are some conspiracists who are saying this, that really the hospital situation is far from critical, I would suppose. So, but here in Washington State, they basically have things and deaths under control. It's pretty flat, right? A lot of other places are getting a lot more out of control. But that's my own personal experience. The hospitals seem to be doing a good job keeping up with it. But that's not that's a little bit on the COVID news there. But let's get on to what I call the mailbag. So you guys are now. It looks like I can have up to 8 people in the chat. It used to be 6. So I'm going to keep you guys in the chat here, and if anybody else wants to enter into the live room, you'll probably have to send a comment, and then I'll have to see whether one of you other guys want to just temporarily drop out if someone else wants to do a live comment, okay? But otherwise, you guys are welcome to hang out there. So let's get to the mail. So a big topic on the mail is something called displacement current. So I'm just going to share my screen here. And I'm just way behind on my mail here. So Bill, I don't know how you handle it, but it's today I've got 251 mail messages sitting at me. And a lot of them are on this whole displacement current thing here. Okay, so a little background. Okay, so what is displacement current and why are we talking about it? Now, we were talking about the whole electromagnetic wave equation and what it is. Now, I don't 100% understand what this whole deal about displacement current is, because I'm not a mathematician. So we have the EM wave equation, which says that the electromagnetic wave consists of an electric field and a magnetic field. And I'm sure you've probably seen the pictures about that. So let's go just take a quick look at one of those kind of pictures there. So I'm going to go ahead and share my entire screen here. So you can see everything. So let's see what Google has to say about displacement current. So it's a displacement current density has the same units as electric current density and is a source of magnetic field, just as actual current is. However, it is not an electric current of moving charges, but a time-varying electric field. Okay, so it's a time-varying electric field. Well, that is definitely what they think an electromagnetic wave is, which is a time-varying electric field. And this idea was conceived by James Clerk Maxwell on his paper on physical lines of force in connection with the displacement of electric particles in a dielectric medium. Maxwell added displacement current to the electric current term in Ampere's circular law, dynamical theory of electromagnetic fields. And the derivation is now generally accepted as a historical landmark in physics by virtue of uniting electricity, magnetism, and optics into one single unified theory. And the displacement current term is now seen as a crucial addition that completed Maxwell's equations and is necessary to explain many phenomena, most particularly the existence of electromagnetic waves. So that's something about displacement current. Now, I also heard that displacement current has something to do with electricity that runs through a capacitor. So I wonder if they mentioned that in here. Because certainly in a capacitor, what you have is basically, two wires which are not connected, and they're connected to the plates of a capacitor, but you can still run current, a moving current through that capacitor.
Yes, I think that's primarily where the term displacement comes from. It's an effective displacement of the charges rather than they're running through the medium.
Yeah, so here it is. So they have the illustration here. An example illustrating the need for displacement current arises in connection with capacitors with no medium between the plates. So there you have your capacitor, but yet we can see a current, basically on the left-hand side and running out of the right-hand side, as long as it's charging and discharging the capacitor. So that I get, right? That's definitely a physical phenomenon. And I feel that is due to when the charge accumulates on one plate, it attracts the charges out of the wire of the other plate. And that is how the current actually leaps from one side of the wire to the other because of these accumulating charges on the plate. So the analogy that I have, like with water, is that if you had water pipe entering into a sphere, and there's a water pipe on the other side of the sphere. So obviously, if you put water in one side of the sphere, it's going to come out the other. So that's regular current. But if you put like a rubber bladder through the middle of the sphere, then you can see that as you pump water into that bladder sphere thing, that it's going to push the bladder out, and then that's going to cause a current. But it can't keep it up forever because eventually the bladder, is compressed too much. But then it can come back, and you can see the flow go the other way. So that is like the water analogy for how displacement current works in capacitors. So even though there's that rubber diaphragm that prevents free flow of water between the two pipes, a current of water can still flow as long as it's kind of like moving, right? As long as it's moving, you can get this flow of water that's limited. So I'm not exactly sure what the relationship is between that displacement current and the displacement current that they're talking about in the electromagnetic wave. So I'm kind of wondering whether they mentioned that. Or maybe they explain the displacement current, not the way that I explain. Maybe that's, but in terms of, say, all of this math, right? They're using Gauss's law. They're using magnetic fields and magnetic constants and all of that stuff. But it would seem that the explanation I gave doesn't require any of that, right? It's just charges accumulating on the plate. So I would kind of have to doubt all of this math, really. I mean, it may actually work out this way, but not because of the interaction of magnetic fields. Now, the other problem is that I'll mention is that if this is displacement current, then where's the equivalent of the charged plate in the middle of free space, right? If this is happening, like if I transmit a signal from the Earth to the moon, there is no series of capacitor plates between the Earth and the moon to carry that radio signal all the way over there, right? So how is it possible that they can apply this law to that phenomenon?
Well, to my mind, this is where you need to postulate that there's a dielectric between the Earth and the moon, or maybe a number of dielectrics, which is basically the ether. It's the medium.
It could be. I mean, I have heard some people propose effectively some idea like that, like, space is filled with capacitors, right?
And that's why the permittivity comes in, because that's the dielectric constant of the ether, which governs the magnitude of the displacement current.
Yeah, that's an interesting concept. I mean, me personally, I think the ether itself is obviously a dielectric, but it's because I think the ether is just a dipole of positive and negative charges. That's all I think it is. So that's definitely a dielectric, but it's definitely not a capacitor, right? Capacitors are made out of materials which can hold variable amounts of electrons. And there's no way that an individual electron could hold more electrons. I mean, it's just, can only hold one unit of charge in there, right? The only thing that might change is, say, the distance between the charges. So in any case, so that's a little background on what the heck displacement current is, to give you some background on what these people are talking about, right? So let's get to the first message here. Let's see here, recent message. I haven't read any of these. Let's see what happens. So it says, hi, Akimbo, when you started to take the curl of the EM equations, your argument degenerated into total nonsense. Okay, the maximum information about the nature of space is to be found in the two curl equations, and especially with respect to the vector A, which you avoid. So A is another magnetic vector. EM wave equations involve taking even more curls, and so apart from having established the form of a wave equation, we are no more likely to establish the physical nature of the displacement mechanism than we are with the original contradictory curl equations, and indeed less likely. To start talking the curl again in hopes that this will reveal some of the secrets is the height of nonsense. Well, I don't know about you, but I have a hard time talking about the concepts of, say, curl. And curl has something to do with basically forces at right angles to what you would normally consider the main way the vector is pointing, right? So if you think of a magnet, and normally the magnetic vectors are normally considered going from pole to pole, from north to south. But the curl of that would be if you had a force that went around the axis, like a solenoid around a nail. That would kind of be the curl, right? But let's see here. Akimbo saying, I don't normally approve of people who paint graffiti on public spaces. So not exactly respectful. In that case, what is the point of defacing the whole place, having agreed that there's no need to present your model of how displacement current works in EM waves to others on the grounds that I have rejected this model? And where did that start from? Because I don't normally approve of interspersed responses. I'm going to do one in red for your mail to Harry below because some important points need to be highlighted. So what does Harry says? It says your expressed agreement that what is produced at an antenna on signal reception is electric current. Thank you. Yes, I think that's what we can all agree to, that when radio wave hits an antenna, what we are measuring is electric current. All right? We're not measuring electric field. We're not measuring magnetic field. What we're measuring is, in fact, an oscillating current.
Harry? Harry?
Is Harry here?
No? Okay, how about Franklin?
Of course, I'm here.
Franklin, I'm wondering if your premise of let's read your emails is actually appropriate here. If I'm sending you emails, perhaps I'm assuming some kind of confidentiality between you and I, even if I don't explicitly state it. So unless you have already previewed these emails or gotten the permission from the sender, I'm wondering if it's appropriate to actually read these.
I think it is because
this is actually being recorded, you know.
Yes, it is. I think it is because if you look at this gigantic email list, you know, these people obviously have no concept of privacy. Anyway, I mean, basically, anyone who writes to this email list wants it to go out to as many people as possible. This also goes out to any mail message that goes through this also goes to the NPA relativity Google groups.
So this is an email list, not your personal private email.
Yeah, this is just a gigantic email list that's been floating around with the NPS for years, really. I mean, and this, in fact, this entire science chat was kind of born out of this email list that was created originally by the guy who did the original science chats. And yeah, he just like got every single email he could possibly find, clubbed them all together, and it's been going on ever since. So,
okay, never mind.
But it's an interesting point. So, but if anyone who's watching this is offended by bringing things up, then well, sorry, and you can let me know, or you can try and take yourself off this list, which is actually quite difficult. But if I see anything personal about someone's girlfriend, I won't read that. But that never happens. It's all this boring stuff about electromagnetic waves and the things that people are actively discussing. And like I said, I'm just kind of trying this out the mail bay because I haven't had a chance to actually read my email. So I'm trying to catch up what's going on here and keep you guys informed at the same time.
Well,
But
if you'll notice the discussion of displacement current in the email threads is between a handful of people and like nothing else, which is very unusual, is being discussed by anybody else. It's like very quiet as far as the email threads are concerned.
Quiet? In what way?
Well, usually there's several different topics authored by many different people. Right now, there's basically for the last 2 weeks been displacement current by a handful of people, and that's it. It's kind of weird.
Well, no, that's actually fairly typical that only about, only 3 or 4 people generate like 95% of the messages. That's fairly typical. The main co-conspirators this time around would be myself and Cornelius, Akimbo, Harry, and David. So that seems to be the main people involved in this very, very rigorous and contentious discussion here. That goes on forever, really. Really, it goes on forever. People are replying like all over the place. But there are a number of the topics of discussion here. So, but the key here is that the use of power density per unit point detectors are useful for the further technical applications, but do not detract from the fact that what is produced in the antenna on the receiving end is an electric current. This fact is experimentally established by the work of Faraday, Ampere, Oersted, etc. This experimental work was then converted into mathematical form, which are the two Curl equations as stated by blah, blah, blah. Okay, these Curl equations can codify reciprocal experimental facts, and he's saying they are not reciprocal, i.e. the time-varying magnetic field causes electric current in a nearby conductor. Correct, that's magnetic induction, and time-varying electric field causes a magnetic current in nearby space. Now he's saying something about the Curl equations, purely a relationship between electric current and magnetic field. It applies to steady state, of course, also in the dynamic state. Therefore, what would cause a current in antenna based on the facts of an experiment is a time-varying magnetic field. He's saying that's correct. An electric field cannot cause an electric current in an antenna. Yes, it can, and that electric field is induced by a changing magnetic field. Well, I don't know that that's true. You can create a time-varying electric field without a changing magnetic field. Talk less of a time-varying electric field. Well, of course, electric field being time-varying merely incidentally related to electric field causing electric current. Electricity cannot give rise to electricity. Let's see, who's talking here? So this is...
By the way, just while you're looking at that, I have a comment in a second, but I just mentioned for the information of anybody who's interested that I got off this list in this fashion because I've noticed some people have, written in and said, could you please remove me? And nothing happens. Well, actually, I'm a bit sorry that I haven't seen this, and I must go into the CNPS list. I can maybe have a look at some of these emails, but the way I got out of this is my email address changed in March. The previous one has been discontinued, so they don't have my new email address. It's obviously sent to my old one, which is just bouncing. But anyway, the comment I was going to make, Franklin, was this, that if you consider the four fundamental Maxwell equations, the two divergence equations and the two Curl equations, well, they're not actually independent. The divergence equations follow from the Curl equations. So the Curl equations are basically the fundamental equations. Now, the asymmetry arises from the divergence of the electric field being non-zero, being basically related to the charge density, but the divergence of the magnetic induction being zero. So if you then go to the Curl equations and you take the divergence of, say, the rate of change of magnetic induction, well, you get the divergence of a curl on the other side because that's related to the curl of the E field. The divergence of a curl is always zero. That's a mathematical identity. So, that equation works out. You would get that div B equals 0. But if you do the same for the Curl equation of the Ampere law without the displacement current, you would get that div E equals 0. So in order for the divergence of E to be equal to rho over epsilon naught, you have to have another term. And that turns out to be the displacement current, because if you postulate this displacement current, this delta d by delta t, you get a divergence of rho, which is basically the current density. So that's the displacement current density. Now, I don't know if that's clear. You would really need to look at the equations. But in a nutshell, the equations are not independent. There are only two independent equations, the curl equations, and they would be inconsistent. Well, the magnetic one would be consistent, but the electric one wouldn't be consistent with the divergence equations unless you introduced the displacement current.
Well, as you suspect, I was completely lost about that entire discussion. It's like when I look at physics papers and they have all those equations with the deltas and the ats and all the Greek letters. It might as well be totally in Greek anyways. But that's just me. I mean, some people are skilled in working those equations, and I'm just not one of them. So.
But of course, although I'm a mathematician, I always maintain that mathematics should be capable of being described in ordinary language. And maybe the simplest way to do that would be to say, well, look, according to the conventional classical system, there are no magnetic monopoles, whereas there are electric monopoles. You know, the charge occurs either positive or negative. It can do that alone. And therefore, there's an asymmetry between the two. And unless you introduce, if you didn't introduce electric displacement, well, then that would insist upon there being no electric monopoles, which we know in practice is incorrect. So in order for there to be a possibility of having electric monopoles, charges in isolation, you have to introduce that displacement current. So that's trying to explain in English what we were saying in mathematics.
Well, I mean, try and explain that again, because I don't get that connection. I mean, what does having a electric monopole have to do with displacement current? I mean, I see no connection.
Yeah. Well, you see, I might have to mix the two then, Franklin. You know, the mathematics and the English. The divergence of the magnetic induction being zero means that there are no magnetic monopoles.
Well, let's talk about that. So the divergence of the magnetic field. So that is like if I have a magnet and it's circular, and if you were to look at the magnetic field, it gets weaker as it goes away from the magnet. If you were to measure the amount it gets weaker, we call that divergence. Or well, I don't know, literally divergence is if you were to draw out the magnetic fields lines. Does it have to do with the spreading? But I think it has to do with the rate that it decreases.
They must ultimately curl back upon themselves. They cannot diverge to infinity. They must be closed loops.
Is that, well, what does that have to do with divergence? Because I never heard of divergence.
So the divergence is zero. If the divergence were non-zero, well, then it would be radiating out.
Okay, that's what you mean by divergence must be zero, which means that the lines must close back upon themselves, right?
Yeah. So you can see how that happens with
that goes out must go back in, kind of thing.
Yeah.
As opposed to an electric charge, which has infinite divergence. Would that be correct? Electric charge.
Yes, because once you have an electric charge there, the field just diverges out and it doesn't close in upon itself if you have a single electric charge.
Okay. So
by the way, just a matter of interest, Bill Lucas has put a comment in, which you've probably seen, just to say that he can buy in China magnetic monopoles and their fridge magnets and so on. That's an interesting comment, actually. But we're talking about classical physics now. Without these devices, I don't know where they come from, but that's another detail.
Yeah, I'm just trying to understand what you're talking about there. So I think I got the divergence part. Okay, so magnetic fields have zero divergence. They always curl back into each other. Yeah. Okay. So
that's the first of the equations, or the third of the equations, or the second of the equations, maybe Maxwell's equations. That the divergence of B is equal to zero. So that's all that means.
Really, I mean, but they always show like say between the north and the south pole of a bar magnet, the magnetic fields are always shown in one direction from one pole to the other, right? So how can the divergence of that be zero? I mean, it's coming out of one magnet and going into the other, right? It's not looping back on itself. Or is it? What do you think?
It is, surely. It's not spreading out into space. It's they're closed loops, basically. As distinct from, you see the picture with a charge, a point charge, a positive point charge, with all the lines radiating out in all directions. And there the divergence is non-zero of that field.
Well, I would think the divergence would be non-zero in the case of two bar magnets sitting next to each other, where the magnetic field is like coming out of one bar and pointing in the other. So I don't think that is.
Well, maybe this is the way that Bill Lucas's magnetic monopoles work. I don't know how they work, but if we take a simple bar magnet with a north and south pole,
yeah, that clearly has a divergence of zero.
Okay, that's all we need to accept. Fine. So
I'm not sure I need to accept, but okay, given that, and the differences between a bar magnet and a isolated charge, so what does that have to do with displacement current? Let's get that.
Okay, now that's the next. So we've got stage one correct now.
Stage
now
one.
We need to go to stage two. There are two stages in this process, and the second phase, the second stage, is related to the curl, the rotation of these vectors. In continental Europe, they call it rot A instead of curl A, the rotation of A. So
yeah, what do you call about rotation? Because I don't see anything rotating in the system. Bar magnet or charge, no rotation that I can see that's apparent. So what do they mean by curl?
Okay, I'm trying to translate the mathematics now into language. So if you look at the Faraday induction law, it says that the rotation or the curl of the electric field is proportional to the rate of change, the time rate of change of the magnetic field. Okay?
What? That doesn't make any sense. I have got an electric charge. It's emanating the electric field. No magnetic field to be seen there. So how can you say the curl is the rate of change of the magnetic field, which doesn't exist?
No, if there is a magnetic field there which is varying in time. So, okay, you can switch around left and right sides of the equation. But let's take the magnetic field as existing. It's created in some way or other. And it's changing in time. Well, that's related to the circulation of the E field. Now, it's true, you're looking at it from the other way around. It's true that the essential Faraday's law would basically say that the rate of change of flux would give you an electromotive force. That's basically the elementary way of looking at that. Well, this is the same. You've just fiddled around a bit, and you've said the rate of change of the magnetic induction is proportional to the circulation of the electric field. It's the same thing.
Not quite sure. I mean, I understand magnetic induction. So if I have a bar magnet and I'm just kind of waving it around, and if I have a measuring device somewhere in the vicinity, it will measure a time-varying magnetic field, right, as I'm kind of waving it around. And that time-varying magnetic field, if I put a wire somewhere in that area, I will see that that varying magnetic field will generate an electric current. Now, I get that. And now you're saying there is some kind of reverse thing. And I understand that the reverse thing is that if you had the wire, if you took away the magnet, and if you put a time-varying electric field in the wire, then you get a corresponding time-varying magnetic field somewhere out in space. Is that the reverse you're talking about?
Well, I think you've skipped a step there. I mean, that's the next step we're coming to now, because that's the Ampere law. But we've dealt with the first two equations in language, and now we're dealing with the third equation. you're skipping to the fourth equation. If we could just stick to the third equation, which is basically Faraday's induction law, which you say you understand how, the change, the flux changing of the magnetic field will generate an electromotive force, will generate a voltage. So that's basically the way we describe the induction law, and you've given some physical considerations to it. Well, the curl equation is just another way of expressing that. Now you were skipping a moment ago to the fourth equation. We can come to that when you're ready.
I mean, this is key to this whole discussion because people are thinking that the reception of a radio wave is like an induction event. Literally, like you wave a magnet around a wire and a current is induced upon the wire, right? And that would be the key thing here. So I think that's what they were talking about here in the email, and that they're saying that if this is the case, then it is in fact the magnetic induction which is causing the current to appear. And that it didn't really have anything to do with, say, the electric current at all. I think that was the point, that the electric current was kind of coming, electric field was kind of coming along for the ride for no good reason, because a time-varying electric field does not generate an EMF to a magnetic field, I suppose, right? I mean, do you agree with that? Is that a reasonable presumption that the reception of a radio wave is an induction event, that it's testing the magnetic field and it's responding to just that? I mean, that's the mainstream interpretation.
I don't know about that. I might have to give that a bit more thought, because I haven't been privy to the email list. I haven't seen them, so I'm not quite sure the arguments. I mean, some of the people there are generally quite logical thinkers. Harry and David and Akimbo and was there somebody else? They're all pretty logical thinkers, and sometimes they get a bit heated in their arguments, and that's one of the reasons I'm not really very enthusiastic about getting involved in these discussions. But nevertheless, they are quite fundamental. I'm
just asking a basic question: is the reception of a radio wave due to magnetic induction? Is that a reasonable presumption in your opinion? So you can either say that's reasonable or it's not reasonable.
I think that's probably part of it. I mean, magnetic induction and electric induction come together, and they are responsible for radio communication. Yes, I would accept that.
Well, actually, so my point is that I completely disagree with that. So just to give you the alternative, see, when I respond, I'm going to respond saying that you guys are all crazy, right? That I repeatedly argued that the reception of a radio wave signal does not prove that was caused by a magnetic field. So while, one of the things I'm going to respond to is, Harry is saying, the facts of the experiment prove that there's a magnetic field because we received that in the electrical conductor, right? So that must have been caused by a magnetic field. And I'm saying no such thing. All we know is that there's something called a wave, a magnetic wave. It hits metals, and we see it create the electric current. That's what you saw in the email there. Say we all agree that the end result is an electric current, right? But that's not to say what happens in the middle of free space, right? Between the Earth and the Moon. What's going on there? Now, while it would be consistent, I mean, I'm saying it's consistent. It's not unreasonable to think that electric current that we're observing at the metal rod is due to magnetic induction, and clearly it can work that way. Like I said, if I had a magnet and I had like a radio antenna and I waved the magnet around, I should be able to measure a electric current coming out of the rod due to normal induction. But I disagree with that because that effect, that is what drives, say, transformers. Transformers work by direct interaction of a changing magnetic field is basically what's going on there. But we know that that's not radio waves. What goes on inside of a transformer is not because a radio wave is being transmitted from one coil to the other. And we cannot create radio transmitters using just using these variable magnetic fields. We can generate interesting induction effects, like at MIT, they demonstrated that you can transmit a significant amount of power from one coil, induction coil, to a receiving induction coil, and enough to light a light bulb. But those effects, as found out by the early radio pioneers, is very, very short range. You can only go like maybe 10 feet or so to be effective, but you cannot transmit like hundreds, or to thousands of miles using these kind of inductive effects. Inductive effects are very, very short range. So I do not think that, it may be consistent that a magnetic field is creating, the observed electric current, but it's grossly insufficient to say that that's what's happening. So in all of my emails, I keep on pointing out that nobody has ever measured the time-varying electric and magnetic field in free space. They've always accepted that, well, because it hits the rod antenna and it creates voltage, that must mean that magnetic field and that electric field had to exist, because after all, how else could it create the electric current if not by, magnetic induction? And, to that, I've been trying to propose my own different way of it happening, right? Now, if that was the only way that an electric current could be generated on a rod, then that might be true, if that was like the only way. But, there are other ways. For example, if I were to, say, shoot a CRT beam at the electric antenna, I could shove electrons into that rod remotely and cause it to have a time-varying voltage. Now, does that prove that the CRT beam, that is a time-varying magnetic field? No, it doesn't. It absolutely does not. There could be other mechanisms by which that electric current was generated. The other counterexample I would put up is that, say you have a speaker and you have a microphone. And, I turn on the speaker and then it activates the microphone. And when we measure what's happening, we can see a current coming out of the microphone. Now, by the same logic that, like Harry is using, because we see the electric current, that proves that the thing that's transmitting is this electromagnetic wave. Well, there's no way you can separate that logic from the logic between the speaker and the microphone, because once again, you can look at it the same way and say, oh, look, the microphone is generating a varying electric field, electric voltage, and therefore the thing that's transmitting it must be an electromagnetic wave, right? So you have to conclude that my sound wave coming at you is coming out by the virtue of a magnetic, time-varying magnetic and electric field, because the thing that's receiving it is responding to it by creating electric voltage, right? So that would be, is that a fair argument for saying that the reception of a radio wave does not prove by itself that it's from a time-varying magnetic field, I guess is what I'm saying. So what do you guys think of that? Is that a fair argument? Maybe Bill, do you think that that's a fair argument to say that it's not proven that radio reception is magnetic induction necessarily. I think you're muted there, Bill. Well, actually, you don't seem to have a microphone. No, there you go. You got a microphone. I guess Mike is having a little bit of a problem there. Maybe Bob, you might want to maybe chime in on this. I mean, I'm just kind of wondering whether.
I think I hear Bill now.
Can you hear me, Bill?
Okay, we can kind of hear you now, Bill.
Can you hear me now?
It's
Little
a little
bit.
faint.
I wanted to make some comments that no one has made, and that is the role of politics in science. And in the case of electrodynamics, Maxwell had 8 empirical equations. But after Maxwell died and Oliver Heaviside took over, he reduced that to 4. And he did that to correspond to the newly accepted philosophy of science, or new scientific method called the existential scientific method, which removed the role of logic from the scientific method. And by the existential method, which we use today in science, you have a hypothesis and you see if the hypothesis can predict data, but you don't look at the assumptions.
But Bill, I do want you to stay on topic, please.
Okay.
Yeah, I need you to stay on topic here. Specifically,
so
do antennas work by magnetic induction?
Those equations we were looking at were incomplete, from which we defined the displacement current. There are 8 equations. When you solve the 8 simultaneously, as I do in my book, The Universal Force, Volume 1, you see that you can explain all the results of special relativity and general relativity, but not using those theories or their assumptions. You don't use any additional assumptions, you just use the empirical laws of electrodynamics. And I want to show, for everyone to see right now, I have here a metal plate from one of my computers, and this is a magnet. This is a monopole magnet. You can see what it looks like on both sides. And this magnet, if I put it on here with the dark side down, it stays on the metal. If I turn it over and let go, it drops. There's no magnetic field coming out. Now, that can't be a dipole magnet. If it was a dipole magnet, it would work on both sides. And you have these in your house. They're called refrigerator magnets. And you'll see that some refrigerator magnets are real dipole magnets, but there are many of them that are monopole magnets. And you'll see that. And you'll see that the abbreviated set of the empirical equations of electrodynamics that Oliver Heaviside adopted to correspond with the existential philosophy of science, it is false. It cannot produce the results of quantum mechanics, which the complete set of 8 equations can produce all the quantum effects, including describing many more transitions in the atom than the set that Oliver Heaviside was working with.
Well, Bill, I'm going to have to stop you right there because I can't, because we've got to stay kind of on topic here, right? Now, that's great that,
Okay, so I'm saying the displacement
are wrong, but none of that is going to give us any insight onto how a radio receiver works, which is what we're fundamentally trying to get at here. So unless what you're saying has some relevance to how that works, that's what I'm trying to get at. That's the topic here. So that's why I was asking you just for your opinion about how a radio wave is actually received upon a receiving antenna. I mean, is the mechanism induction? That's what I was asking about. I think And
You've
anybody
got
else?
to look at Lenz's law. And see, Lenz's law was taken out of the fundamental equations of Maxwell had done, and it describes these phenomena. And when you take it out, you now have to invent a displacement current because you don't have a way to describe it. Because you took it away when you got rid of Lenz's law. And
Well, I don't think you have to use basically any of these laws. So, Andreas, he has a comment here, which I am sympathetic with, which is that I am under the impression radio wave induction is due to collisions only and resulting jostled electrons.
when you look at that statement that he just made, where is the role of logic coming in? Can you describe what you're seeing logically with the fundamental empirical equations of electrodynamics?
I would say yes. I mean, as a mechanical person, so I'm sympathetic to mechanical explanations, and I understand how collisions work, right? So that has been the explanation that I have been putting forth. It's not magnetic induction that's causing the electric current. What is causing the electric current is actually a physical collision. So a wave is a compression wave. It's made out of matter particles. Literally everything is bathed in a sea of, say, electrons or protons or something. Doesn't necessarily have to be electrons. It could be neutrons. Could be something. So it could be some mystery particle. Whatever it is. When we have a radio wave, that would be the medium for the radio waves. And when the radio wave is transmitted, it creates a compression wave, right? Just like a sound wave creates a back and forth literal pushing, just like between a speaker and a microphone. The hypothesis is that directly pushes on the surface of the electrons, and in a collision pushes them in, right? And then when you take electrons on a metal surface and you push them in, then that's going to increase the voltage in the electric rod, which you can then measure and amplify and turn it into a signal that we can hear as say, sound, like when we transmit radio waves, right? So that is my alternative explanation to how that radio wave gets received by the antenna. That, no one in the mainstream will support me on that. That's why Harry keeps on saying that I'm wrong, because the mainstream does not say that. But, there's a difference between me being wrong just because it's against the mainstream, and me being wrong because it logically doesn't work. So you speak about the role of logic. So to me, in a mechanical universe, that makes total sense, right? Does that not make mechanical sense that it's just a literal pushing of the electrons in the rod, and they just are just creating electric current that way versus?
Let me tell you that you can't explain that way. There are two types of electromagnetic radiation: transverse and longitudinal. How can you explain the difference?
Well, the mainstream doesn't actually recognize that. So that's like, you're like asking me, well, how can you explain the difference between the Easter Bunny and Santa Claus, right? And
my books on
recognized.
electrodynamics do recognize the existence of longitudinal radiation. My book here by Jackson, considered the most common book on classical electrodynamics, and it recognizes longitudinal and transverse radiation. And Jackson has sold more books on electrodynamics than anyone else in the history of the world. So it is known in the politically correct places. I've used Jackson's book in major universities: University of Maryland, Catholic University, College of William and Mary.
But the thing is that I've looked at that, and what they're talking about is longitudinal wave is not the same, longitudinal life energy wave that you also refer to, right? It's just that what they're talking about, I mean, I've looked at that, and that's very specific, and those can be described, once again, I mean, as a type of wave, right? And a type of compression wave.
That's not true. I sell on the internet devices that can detect longitudinal radiation and create longitudinal radiation.
And once again, it's like we don't have any confirmation of that. All we know is that you have a device that receives some kind of radiation and some kind of device that generates something. That it you know, based on your stories, you know, it may be related something to, like, say, you relating it to like microwaves. Microwaves seem to be related to this sort of phenomenon. But once again, those are, it's kind of unknown, I guess. But that really doesn't have any impact upon what I'm saying, that when we're dealing with regular radio waves, right? Let's talk about radio waves. Right? I can generate them using my 101 electronics kit. It's not that tough. All you do is generate a time varying voltage. You put it into a rod, and then some distance away you can recover that signal, right? Now,
if you go online, you'll hear this. You can look up the story of Anton Prior during World War II. He was
we've heard that story, but the thing is that
he was working on a radar antenna, and it put off both types of radiation the same way.
It's not contradictory. I mean, whatever that is, it's in addition to what the fundamental transmission and reception mechanism is, right? I mean, you could say that same argument against the mainstream interpretation, which is it's magnetic induction, right? I mean, that it's like what you're talking about there is off on left field, right? I think.
Well,
so, I mean, it may be a point, but it's
transmission using either transverse radiation or longitudinal or both.
Well, that may be, but once again,
but your explanation won't explain this other phenomenon. You have to be able to have a consistent, logically consistent approach that explains all the data. If you only are explaining the personal data you want to select and say, oh, the rest of it's just nothing. You can do that, but it isn't going to give you any truth in science. You got to have some mechanism to keep the truth, and that mechanism is logic. And that was what was taken out of the scientific method in the 1860s when we changed to the existential scientific method. And of course, now we're using the postmodern scientific method, which is the existential method, but each field of natural philosophy has a separate silo, and what is learned in one is not applied in the other. And so we no longer have a university, we have a multiversity, because each field is independent of the other. They only can cooperate to the extent they want to, but they don't have to. So for instance, the force of gravity was discovered to be electromagnetic by the chemistry silo, but we don't recognize it in physics. We don't recognize that gravity is an electromagnetic phenomenon. And we can prove it if we want to, but we don't want to use logic. We don't want to do that sort of thing. We want to be able to make the results of science politically correct by our current political views. And that is what is a shame, because it keeps us from making real progress in science. And all the major theories in modern science since the 1860s are false. That includes quantum.
Now, I see you have some comments from Alistair. Alistair, do you want to go ahead and respond to Bill? Alistair, you there? I see you have some interesting comments here. Alistair saying that book sales or popularity are not an indication of established fact. If it was, creation and Noah's Ark would be fact and not fiction. Although if you talk to religious people, they probably think that is fact. But Roger, you're waving your hand. Did you want to make a comment? again, this is an open discussion. I'm just
Hello.
starting things here. So
Can
Yeah,
you
we
hear
hear
me? Oh, great. I'm wondering, is it what Bill's talking about to do with the X Club? Has he heard of the X Club?
the X Club?
Can you link to
I
my
don't know what
can I
the
show
X
my
Club
computer
is.
screen? Yeah, can you display my
Anyone can
computer screen?
share their screen. I can stop sharing the screen. On the bottom, there's a share screen button. You click on it.
Yeah.
You
Can
click
share
on it,
my
and then you
screen?
have to click on the show all display thing, and then click OK. Then we can see your screen.
Just great. Right.
Are you going to show us something about this X thing?
X Club, is it? Your screen. Yeah.
But just to kind of respond to Bill's response,
Right.
because I know
Okay.
that a lot of people will do this, even mainstream. It says that you can't have
No,
a
that
theory
says
without
that.
explaining 100% of everything. And I say, well, eventually you should be able to explain it. Eventually I should be able to explain by my collisional theory of radio reception what he's talking about with longitudinal and transverse waves. Yes, we should be able to do that. To say that it can't, I would say is wrong. It's like I'd have to take a look at it, and then maybe I could. And maybe the explanation is a lot simpler than what we currently know about, and might be able to reveal exactly what your longitudinal life waves actually are. Maybe they're not radio waves, or maybe they are a certain type of radio wave. Maybe they're at a certain frequency. Maybe they have certain characteristics. But ultimately, you can't say that doesn't work. Maybe it does work. You got to think about it a little bit and figure out what you're exactly talking about. Like for your longitudinal life receiver, you have to look at what that thing is, which is basically a capacitor, right? The longitudinal life receiver is basically you're measuring what's going on with capacitance going on in space, right? So that could be something that's more actually related to an electric and magnetic field, but not necessarily a radio reception. What you're talking about could actually be completely divorced from radio waves and electromagnetic spectrum. It could be, in which case, what I'm talking about as far as the collisional theory of radio reception, that's like me explaining, why is the sky blue, right? It's like, does my explanation have to explain, why is the sky blue? Well, that certainly needs to be explained, but it's certainly probably outside of the realm of what I'm talking about here. So you just can't go and throw every other little, or explain like how refrigerator magnets work. So your theory is wrong, but you can't explain how refrigerator magnets work. So that may have nothing to do with radio reception, okay? So you just can't go throwing around different things. That's why I want to keep you on topic, right? Because I asked you this very specific question about, is radio reception due to magnetic induction? That's a very simple, straight question. I just want an answer as to whether you agree with the mainstream that it is, or whether you agree with the crazy people like myself who disagree and think that it's actually more of a mechanical kind of thing. It's literal hitting of something. I think we have James here. James, do you have any comments about, how does radio reception actually work? What is going on with the antenna? I claim it's a actual impact to the antenna. In one of my email messages, I said it's like you take a rod and you hit it with a hammer. I'm sure if you do that, you will see some voltage variation going on in the rod from the electrons literally being compressed by the hammer. And that doesn't have anything to do with magnetic induction. No comments on this, James? You can hear me, right? Or maybe Bob. Bob, you were trying to say something a little bit earlier. Did you have any comments on this?
James, your mic is off. And yes, I do have a comment.
Well,
Just
why
use
don't you go
Weber.
ahead? Why don't you go ahead, Bob, and then we'll let James talk.
Should I go ahead? Oh, okay.
Well, my comment was just use Weber. And it has one equation, and then the logic from that one equation, which was derived from empirical data, one equation, then use mathematical logic. The logic is the mathematical derivations, and you can derive all of the classical electrodynamics from that. And by classical, I mean excluding the special theory of relativity. But some people seem to think they can stick that into Weber as well.
But does that make
And so
any
your
sense?
radio, and this, you have a source, a charge of something, and your transmitter, and you're moving that source. Any moving source will cause a force on
No, you're not
some
moving
other.
the source. You're not moving the source. I mean, radio
Yes, you
antenna is
are.
a static item.
That's right. But within that is made up of charged bodies, protons and electrons. You move protons and or electrons, that will cause a force on any other charged body, an electron or a proton, at a distance away from that. And that's all it is. To say this anything in between, yes, you can say that, compression wave, transverse wave, whatever. But the only thing you can really measure is a moving electric charge and interacting with another moving electric charge, a moving charge in the transmitter and a moving charge in the receiver. Anything else is kind of speculation. And you say, oh, I'm going to measure that. What are you going to measure it with? An electric charge, a proton or an electron. You can't get away from that. There's no other way to do any kind of measurement. So all there really is moving charges as a quote unquote source, inducing a force and motion in receiving or test or detector charges. And that's all you can say about it. Anyway, I went even longer than I thought.
Well, I would say that's not exactly true, because this is my main criticism to the electromagnetic wave. You know, they say that in free space, there's going to be this exchange of electric and magnetic fields. You know, as you go through space, there's going to be a magnetic field, let's say, pointing this way, and then when it changes its wave direction, it's going to be pointing that way. So we have this time varying. You should be absolutely be able to measure this magnetic field, which you can see pointing this way, and then pointing that way, and then pointing this way, going and increasing and decreasing in magnitude. You should be able to, for example, place something like a compass in the middle of space, and as I see the electromagnetic wave go by, I should be able to see that compass point this way, and then decrease in strength, and then point this way, and then decrease in strength and point this way.
But the compass is made up of charged bodies. The compass is made up of electrons and protons. You can't get away from that.
That's how we measure a magnetic field directly, right? And that's okay. It doesn't matter that it's what it's made out of. Of course it's made out of.
Yes, it does. It's made out of electrons and protons. And what caused that magnetic wave that you're talking about? Electrons and protons. So
yes,
all you can say is that changing electric, particles will induce a force on other electric particles. That's all you can say.
And I'm also saying that forces on electric particles can be induced by mechanical means, literal collisions. That's another thing that happens. So that's my shtick. It's like, it's when the radio transmitter transmits, it's not due to the influence of its electric field, because electric field is very weak. It's almost completely neutral rod. So you're not gonna, if you take an electrometer around the radio transmitter, you're not going to see very much of a strength difference, at least not one that travels like 50 miles to my TV. There's something else going on here, and I think that that's just an ordinary compression wave. So, Bill, you've had your hand up. Yes, do you have a comment?
I build antenna for radios, and TV. And if you've ever built one, you know that when you put the various pieces of your antenna together, there's a wavelength that is you're headed for. So when I listen to an FM radio station, I know like the wavelength is 89.7 or whatever it is, units there. And if I make the antenna a certain length, I get the highest possible return on those frequencies that have a wavelength equal to that. But if I want to get a different station, it'll have a different frequency. And so I'll have to alter my antenna, or I have to make an antenna that's got a range of pieces to it that will cover the different frequencies. So the explanation you're giving doesn't show how the different links of the part of the radio antenna cause you to get more power. And if it's the wrong link, if it's too long or it's too short, you don't get very much, if any. And
yes, I think it very neatly explains that. I mean, the analogies would be exactly the same as if you were to say, I don't know, have a tube with water in it, and the speed of the propagation speed of the wave down the length of the tube is a resonant frequency, and if you put in frequencies which are not, whole wavelengths down any tube of any medium, you can see that you do not get resonance. So I mean that's just all based on just resonance theory, but that's all I think perfectly consistent with particulate medium kind of physics, right? So yes, that's easily explained, I would say.
Well, if you have particles moving, the wavelength won't be as significant as if you have an electromagnetic wave, which is not made of particles. And so that you have a little bit of trouble if you're using a media that has all these charges in it, and that media is what is transferring the energy. You'll find that in space, where the density of particles is less, you have better transmission and longer distances than you do when you have to deal with the atmosphere and things of that sort. So we can have a small radio antenna on a satellite, taking it out to the edge of our galaxy, and we can easily receive the transmissions back and forth because it doesn't have to go through a media with charged particles. And so
yeah, I think all of that is perfectly consistent with, say, radio or water waves. Those things basically act pretty much the same. I mean, to a large extent, this is one of the reasons why we think radio waves must exist in some particulate medium, right? I mean, there's only two choices. It's like either the radio waves are in a physical medium of some sort, or they're not, right? It's either that they're in some physical medium, or there's something else. Now, they could be something else. It could be like, radio waves are hosted on ghosts or something, having nothing to do with protons or electrons.
Yeah.
Or it could.
Hooper at University of California at Berkeley measured that there is a tensile strength to the electric magnetic field. This tensile strength, no matter how close to a vacuum you put it, is still the same. That cannot.
Is that not evidence that there is a physical substance even in a complete vacuum? Because there exists this tensile strength. The tensile strength is only a property of what we consider, hard materials.
Yeah.
Right?
The other thing is they found that the electric field cannot be cut. It's uncuttable.
Which is probably another.
It can be cut.
Which is probably another property of particulate mediums. I cannot cut the air, generally speaking.
But in space, I don't have any.
No, apparently you do. That's my argument, that there is a actual physical material substance out there in the vacuum of space, which is just as material as my arm. It's just as material as the nose on your face.
But we don't have any experiments to prove that.
Well, we do. I mean, even the mainstream thinks that, there's virtual particles, positrons, electrons, popping in and out of space constantly in this quantum foam. That's what they say.
That theory is false if you use logic. They use the
it's not really false.
If every assumption of your theory is known to be false, that doesn't falsify the theory.
But it's not. It's actually consistent with everything that we know, which we can eject positrons and electrons out of the vacuum in pair production. What is the logical conclusion there?
I do those experiments at the accelerator laboratories, and we don't make them out of nothing. We make them by collision of one particle with another, and that's how we get all these particles out.
Yeah, and the question is, where do those particles come from? I mean, you collide two protons together at extremely high speed.
Elementary particles, which are made of subparticles, and those subparticles are conserved, and we can see what they were, and we can see by what particles come out, how that conservation works, and we can figure out the structure. And I have published the structure of all the known elementary particles in terms of...
So what does logic tell you about that? I mean, you collide basically anything, whether it's protons, whole lead atoms, or even individual electrons. The result is pretty much the same. You get this gigantic spray of mostly like 99.5% positrons and electrons out of these things.
No, that's
sometimes you get interesting particles.
In the experiments I've done at accelerator laboratories like Los Alamos and other places, the Space Radiation Effects Laboratory, we make a beam of protons, and we run that through another beam of protons, and we can see what particles come out. Those particles are the things that the ingredients of the proton, the solitons that make it up, they can come apart and regroup to form different elementary particles, but it conserves the same solitons, and we can actually show what those solitons are and what their properties are and how the geometry by which they go together determines how many of them.
Well, doesn't that all contradict, the main observation that whenever you collide anything together, you get largely positrons and electrons, huge clouds of positrons and electrons, which people like CERN.
I made the measurements using hundreds of instruments on the beams to see all the kinds of things that come out. And there's not a lot of electrons and the positrons.
In fact, I mean, that's basically all CERN is actually looking at. They're only looking at positrons, electrons. This is how they discovered the Higgs boson.
That is not true.
That is true. That's what they're doing. It's an ET
laboratory where I worked and got my PhD in physics. We reproduced the accelerators that were at CERN, which did not work very well. They only had 1,000.
Look, Bill, it's a simple question. When you collide two protons together, what do you mostly see? If you don't filter out anything, what do you mostly see?
A lot of particles.
Yeah, and what are those particles?
Kaons, muons, positrons, electrons.
You see positrons. I mean, you see muons and stuff like that. But by and large, you see a lot of positrons and electrons. Now, logically, I'm asking, well, where did those come from? I mean, if you add up all the mass of all the stuff that comes out of the collision, you'll find out it's more than what you put in, right? No. Now, I would say the logical reason is because you've knocked all those positrons and electrons out of bare space. They were there before. And so there's this huge reservoir of particles that you can get. You collide
the beam of, say, protons in a vacuum. We don't get anything coming out.
Let me get some. You said you get muons and protons and electrons, all kinds of weird particles.
One beam hitting another beam. That way we know we only have two things involved.
Whereas, yes, and when you do that, then you get all these other particles coming out. You get the muons.
They're not the same particles you'd get if you had air in there, because the air would produce you free up a lot of electrons from the molecules of the air. But see, we don't want to have the interference of that, so we do it in a vacuum.
Yeah, and so it's a very good experiment. And I'm just saying that you're saying there's no evidence that space is filled with positrons and electrons or some kind of material matter.
Everything that is made when we have two beams of protons hitting one another, everything can be explained by the subparticles or the smaller particles that make up protons, how they regroup into other particles. And it conserves what we call those, I call those things solitons, and it conserves solitons. We don't make any solitons out of nothing. They are already.
Well, yes, you do. I mean, definitely when you collide two high-speed particles, the mass is
a soliton
mass
is broken up, and it is uncuttable. And
the resultant mass is larger than the. I mean, that's the game that LHC plays all the time. They're just trying to get, because the higher energy they can get, that means the more stuff, more mass, the more massive particles they can create. You know, they can create theoretically the Higgs boson, which is something like 200 times the mass of a proton or something crazy like that. And so, you know, you're colliding something and getting 200 times more mass than you had before, right? Now, it's either you believe in the conversion of energy into mass, which is what mainstream believes, or you can be the crazy dissident like me and say that that mass, that 200 times mass, was knocked out of the existing space, which was largely generated in this gigantic spray of mostly positrons, electrons. So, James, you had a comment.
Yeah, the in Bill's comments, and I give a lot of respect to what he has to say. But my work and opinion is that these high energy proton beams going in opposite directions and colliding head on are really not proton beams. They're actually lepton quark soup, which in the literature is called quark gluon soup. I call it lepton quark soup. Now, in those high energy beams, when you get into the soup energy range, there are not differentiated particles. So the projects at CERN, which are getting over 20 million a year, and that's just from the NSF, and you can go to the nsf.gov website and look this up and see what their budget is. They're actually a little bit mislabeled. They talk about proton-proton collisions at energies where individual beams might be about 7 keV, and with the oncoming two beams, you would double that to in the range of 13 TeV. Those are not protons. Those are soups that you're colliding. And so what Franklin was saying is, how do you get this 200x mass larger particles out of such collisions of protons? It's a mistake to call them proton-proton collisions. You can get these more massive particles out because you're actually not colliding anything that you would call a differentiated proton. You're protons, in plural, I should say. You're actually colliding two soup beams, which are pretty much pure energy without any differentiation or very little differentiation of individual particles such as protons and electrons. End of story.
Well, this
That's my comment.
is based on theories that are politically correct, and the people who do the experiments see it a little differently because they don't always see that their data supports those the correct theories. To say anything about it and keep their job. So I know about that because I worked there at the Space Radiation Effects Laboratory and also at Los Alamos, and that's how they work at those places. And unless you understand the politics of science, you're going to miss that.
Well, if you work there, Bill, then you know that those are not proton beams. They are soup beams. So
And if they are soup beams,
it raises in my mind why you continue to call them proton beams when they're clearly not when those proton beams have energies up to the speed of light, practically the speed of light. There are no differentiated particles. It's pure quanta, pure
Well,
energy
and the
quanta.
proton beams
And
control the energy of the beam, and we can slow the beam down and measure all the properties of the proton. We can speed it up and still measure those same properties, and we can show that there's nothing else there until we make collisions, and then we see something. And so if it was a soup, we would see things.
well, I agree. If you slow the beams down, you might actually be talking about protons and the analysis of the components of protons and so forth that you referred to by analyzing the products of the collisions, and make some sense. I agree with that. However, when you get up highest energies, there are no differentiated particles in there. And anyone working at CERN, in the ALICE project, the CMS project, any of those projects, or the accelerators where you worked, Bill, knows that at those higher energies, you know that you're not dealing with differentiated protons, you're dealing with pure energy beams. And they're called soup beams to distinguish them from, say, proton beams or electron beams.
We're directing these beams.
And you know that, so you don't have to pretend that you know.
We're directing these beams with electromagnets, and also we're getting certain amount of stuff out of the beam if there's any noise or impurities, and so we can see that. We can see the impurities coming out if they're not pure. It's not just all protons or all positrons or pions or kaons. We can make a beam of just pure kaons. In fact, I did kaons, muons, and pions for my thesis, and we made beams and did all kinds of experiments with them. And this idea you have of a soup is not what we saw experimentally. And we did all kinds of measurements. We wanted to know everything that was going on inside of these beams. And we could speed the beam up. We could slow it down. It didn't produce more particles or anything like that.
I would think that the whole physics of colliders absolutely relies upon the proton being an independent, recognizable particle, because that's kind of what we're predicting is colliding. And we predict luminosity that way. And, I have absolutely I've actually never heard of this idea that what goes around in the accelerator is a gluon soup. I mean, there is the term, the plasma gluon soup, which they've been trying to create as a result of these collisions. But I've never heard of anyone describe the particles that go around as being converted into a gluon soup. Plus, I mean, they put all kinds of particles into these accelerators. They put like entire lead atoms into these accelerators. They put protons, neutrons, electrons, all kinds of things. And if they weren't acting as independent particles, then I don't think they could get the results that they're getting. I mean, if it really was a soup, then basically it would just go right past each other, and you'd probably predict there'd be no collision at all. But something is obviously colliding. So it depends extremely upon what you're colliding.
They go right past each other. They form, if they're properly aimed, they form huge jets of dozens of other particles and products, which then decay into other particles. So they don't go right past each other. Oh, no. So when you're talking about the highest energies up to the speed of light, basically there are no slots left which have no energy. It's all pure energy. So there's nothing differentiable in there except pure energy. And that's why we call it soup. Okay? And when they collide, the higher energy that you've got, the more jets, the more particles come out. But I'm repeating myself, so I'll end there.
We use cloud
Now
jets.
look, we got Roger back here. So Roger,
The cloud chamber will show the difference between.
Yeah, we see. I mean, your point is taken. You know, I guess me and Bill disagree, but getting back to Roger. So Roger has been able to put up his. We see your screen now, Roger.
Great.
So you wanted to explain something here?
Great. Yeah. Hold on a minute. Good day. Oops.
Who are we looking at here?
This. Good. This.
Now, does this have to do with our topic, which is we're talking about radio transmission?
It was what Bill was talking about earlier. There was this group of scientists in the 1860s who reformed the Royal Society. They changed what science was supposed to be based upon. So when Bill was saying they abandoned logic, was he sort of referring to the changes this group of men made to science, because they were supposed to be very influential, and they changed what the Royal Society was doing. So
it's their fault.
A key aim was to reform the Royal Society with a view to making the practice science professional. So is that sort of thing, is that what Bill was talking about? This group of men who called themselves the X Society.
Yeah, that's what it was in Great Britain, but
yeah,
in America it comes about from what we call Thomas Jefferson and James Madison got the separation of church and state involved in our Constitution and our Bill of Rights, and there were three groups there, and one of the three groups that they did this to make them happy, they were atheists. They didn't like the church. They didn't like having established churches in the colonies. They didn't like the revivals that were going on in the country and making new churches like Baptist, Presbyterian, Methodist, etc. And so they all were given something with the separation of church and state. And then now, after the 1860s, the federal government was set up to start discriminating in the theories of science. Those that supported the Bible would not receive federal support. Those that denied the truth of the scripture were excluded from the education framework of that's all public schools and schools, colleges, and universities that receive public funds have to obey. Even the religious colleges have to do that. And so that's what's been going on. If you do a little research, the state of California has revealed their education framework to the public, so you can see all the things that in every course from kindergarten through the PhD must be taught to receive federal funds. And I grew up with many people who did not know that when we went to school and got our education, but when we became professors, we found out what we had to do, and we didn't like it, and we stopped teaching. And so because it wasn't true, and that has been going on now for 100 years or more in our country. And all of the major theories of modern science are false, because we changed the scientific method to the existential method and took the role of logic out. And every major theory developed since then are built upon assumptions that are known to be false. And logic says that automatically falsifies the theory, even if it can predict a lot of data. Because it's merely
so that's why we exist here at the CNPS, because we believe that all the major mainstream theories are possibly wrong. Well,
yeah.
You know, but I would say that I still accept Newtonian mechanics and stuff like that. I think everything they invented up to about 1901 was probably okay. But everything after that is probably wrong. You know, everything in quantum atomic field theory is probably wrong. So I'm okay with that. It's like, yeah, I think that that's why we just, because we're looking at that, we're saying that makes no logical sense, right? That's why we're talking about this radio wave thing, because it makes no logical sense that a magnetic field could somehow leap off of one antenna, travel 10,000 miles, and then be received by another receiver. You know, somehow that magnetic field with very short distance has to propagate itself across 10,000 miles and still be receivable. And
Well,
to my mind, there's no logic to that.
What's your explanation, Franklin, as to why everything went awry at the beginning of the 20th century? I mean, Bill has an explanation with regard to conflict between science and religion, but why do you think that things went really bad at the beginning of the 20th century, if they're all right before that?
Well, I think because we actually found we lacked actual things we could actually discover. You know, prior to that, we were making great progress on what electricity does, how radio, making it work, a lot of stuff like that. But about to 1901, you know, with not actually getting to the basic questions like how gravity works or how charge works or how magnetic fields work, we were just stuck. And then we had people like Einstein who come up with these mathematical theories, and then, you know, even though it like completely contradicts every fiber of your body, of your intuition about how these things should work, physics accepted that as long as the math works, then we will accept that. And so now people, when they do physics, it's like, well, show me the math, right? You've got that theory, well, show me the math. It all become about math, but math is divorced from actual physical physics, right? There's things you can write on the board, and then there's things which, you know, actually exist in the world. And I think those two things have just completely divorced each other. But still, even mainstream will admit we still don't know what these fundamental things are. We still don't know what gravity is. We still don't know what charge is. We still don't know what a magnetic field is. And today's discussion, we still don't know what a radio wave is, right? We think we're so modern and so advanced, but yet we have no clue how these forces and fields actually operate, right? My personal opinion is that, you know, it's because we reject the notion of there being an ether, right? It's like, that didn't make any logical sense, right? Logic would tell you, you've got some phenomena, it acts just like a radio wave. What's the easiest way to make that happen? Well, the easiest way to make that happen is if there's some kind of particulate medium in space, but we've rejected that, right? So if you do that, it's like asking someone, okay, play the piano, but do that with your hands tied behind your back. So you're pecking at it with your nose, and you're not going to get very far.
I think that's possibly quite true, but that poses the question as to why we rejected the ether. I mean, that really wasn't rejected, you know, in the 19th century, say the last third of the 19th century, and perhaps it couldn't have been. So I tend to take something from what Bill has been talking about, and I think there might be even slightly fancifully some political connotations. I mean, the fact that there were sort of revolution in the air at the beginning of the 20th century, political revolution, and you know, breaking down what had gone previously. I think that may have led to a new way of thinking, that they couldn't accept the sort of fairly ordered thinking, you know, that had existed before then, the logical sort of Newtonian thinking. They wanted to, you know, go a bit awry. And perhaps we're experiencing a similar movement now, where we want to decry everything from the past. So you get polarized extremes. You know, you get a complete conservatism which won't consider any new ideas, and it's stuck, it's ossified, and there's nothing you can do about that. And then you get the opposite. You get a complete iconoclastic system that wants to destroy everything about the past, including maybe its logical thinking.
Well, I mean, you also have the whole problem is that no one's actually been able to find the ether. I mean, if it exists, then how come no one's been able to find it? I mean, that's a pretty serious problem. And we have the Michelson-Morley experiment, which most people claim, oh, that proves that there is no ether. It's like, no, that just proves that the Michelson-Morley experiment was unable to detect the ether. That's really all that did, but it really didn't. Plus, people don't know, what the ether is. How can you find something you don't know what it is, right? That's like trying to find ghosts.
I'd like to have a comment on someone who reacted at the beginning of the 20th century against this politics and science, and that was Henri Poincaré. And Henri Poincaré he saw the need for fixing science and putting logic back in, and he developed what's called meta theory, which is the theory of theories in natural philosophy. And he put out a number of theorems and proved the theorems from logic. And the theorems invalidated a lot of the major theories. One of the theories it invalidated was Einstein's special and general theory of relativity. And that caused Einstein to never receive a reward for publishing those theories. He did receive a Nobel Prize for his wife's work on the photoelectric effect when she was working at Weber's laboratory, but not for his own work. And that was because they didn't want women to be receiving Nobel Prizes. But because of his work in Europe, Einstein never could get a Nobel Prize for special or general relativity theory. And you think about it, why not? Politically speaking, those are very important theories. And also the theory of quantum mechanics, which was developed after he died, is falsified by the work of Henri Poincaré. So if you want to learn something about this, you can look up some of his books and read those. The most important books he did, which is the proof of the theorems, no library in the world is allowed to let you see those books. Only the books that just talk about the theorem, but don't show the proof of the theorems. And I was amazed to learn that in the United States, I went to University of Maryland, which had the world's largest physics department, and we had a physics library, and I asked to see these things, and the librarian, who was a friend of mine, said, "We cannot show them to you. No one, even the President of the United States, cannot ask to see it and be given permission." And
okay, well, let's get back to our topic here. We do have some comments, so we're getting close to the end of the hour, so I do want to try and get to these comments that we've had come in. And so if you guys have any other comments or watching on the live stream, please feel free to type them in so we can address them. So Scott Ferguson asked, do the electrons wave travel down the wire like water flowing in a pipe, or does the E wave travel on the surface skin and outside the wire? Well, I think I would go with the mainstream answer on this one. And that is that the electrons do travel down a wire like water, but they also travel in waves. Just like if I had a pipe filled with water and I hit one end with a hammer, no water is traveling in the pipe, but yet the wave will travel down that wire. So there's a difference there. And or does the E wave travel on the surface skin and outside the wire? Well, the mainstream will tell us that when you do have flowing electricity, most of the electricity will flow on the outside surface skin, but not necessarily outside the wire. There are some people who think that the electricity actually, like Ivercat, think that the electricity actually flows outside the wire. So me personally, I don't believe that. And once again, here's Harry. Harry always says this is wrong, Franklin. So once again, I think Harry is always confusing me contradicting the mainstream as wrong. So I'm saying that, somebody's wrong. It's either the mainstream's wrong or I'm wrong. But, not necessarily that I'm wrong, right? I guess. Says, we all know empirical laws are dated to be progressive. Induction is a vague term. Of course, there's induction, but what kind of induction? I don't know. What do you mean by there's the we were specifically talking about the magnetic induction on a radio antenna. So Harry objects that in an antenna wire, the current is perpendicular to the direction of the compression wave. So Franklin's theory is false. Okay, let's see. So if this is the radio antenna, the wave comes in this way. So you're expecting the wave, the electric field to go this way? I don't think so, because the wave comes in and it hits the whole surface of the antenna rod, according to my compression hypothesis. That pushes in all the electrons. Now, there's only one place that electrons can actually escape. I mean, and that is if it's attached to some sort of ground, so that the electrons have a place to go. Now, if the antenna was in fact not attached to anything, then the electrons couldn't actually go anywhere. But as long as they're hitting the surface of the wave, any compression will result in a vertical, well, actually, I mean, it doesn't really matter what the way that the antenna is pointing. Any compression on any wire will cause it to be squeezed out the end, right? I mean, you could have an antenna and then have it like curlicued in every which direction, not corresponding at all to the direction of the wave. So therefore, that doesn't disprove my theory at all, I would say. And Ray Carr's comment is that then it would dissipate each time an antenna picked up the signal. And it's like, yes, because that's absolutely what happens, is that when an antenna actually receives and converts that signal, it is absorbed and not available for another antenna to absorb, right? I mean, actually, that's how I think polarizers actually work, because the polarizer is oriented in the same direction as the transmitter. So if we have the transmitter, it looks like this. It radiates, it comes over, it's absorbed by the receiving polarizer. And polarizers are basically just grids of parallel wires. That's what a polarizer in its most basic form is. It's basically just a series of antenna receiving rods in parallel, closely spaced. And what happens is that when it gets a signal which is oriented in the same way as a transmitter, it is absorbed, it's converted into electricity, and is dissipated as heat. And that's fundamentally how a lot of polarizers work. They do that. They observe that, it either reflects it or it's completely absorbed and it's converted into heat. This is what we see with polarizers. And so once again, that is consistent with my hypothesis that it's a collisional, mechanical kind of thing rather than anything having to do with an electric field or magnetic field, which we, like I said, have not measured in free space, right? Because I keep on asking for people, if this electromagnetic wave exists, then we should be able to measure in free space, not at the antenna, right? Because we're talking about a specific thing. Talking about magnetic field, we can definitely measure magnetic fields. In one of my emails, I said, okay, these are you can use a squid to do very precise measurements of a magnetic field. And so we should be able to see these time-varying magnetic fields anywhere we see radio waves, but we do not. We do not measure it, and people don't even seem to be interested in measuring it, right? And you cannot directly tie the electrical current coming out of the antenna rod with this magnetic field that exists like 5,000 miles away, right? Between the Earth and the Moon, out there in the middle between the thing that the theory says exists should be measurable, and it just, no one has. I don't know why people accept this theory. Definitely that predicts that there should be measurable fields out there, but no one has. Everyone just accepts that because we see the reception of the radio wave, that must mean it's magnetic induction, which, like I don't think it is, right? Now, Andreas, for some reason, wants James's opinion. And he is questioning the forbidden literature at UM. Yes, there's forbidden literature that only certain people can get. So I think this is always a test. You should go and try and ask for that book and see whether they can actually find it or not. see what's actually going on here.
Well, I did that, and the person told me that it's locked in a safe, and no one is allowed to use it, to open it. No one. And they must destroy it if they open the safe. So
that's it. We have a couple final. We're getting towards the end of the chat here. We have a few things in the private chat here. Let's see here. How do I do this? I think I got to put these in the main chat for people to see. So, Alistair, you had a couple comments going on here. Did you want to make a live comment about? You were saying a bunch of things about electricity. But it looks like, let's see. Yeah, you have a microphone. So, is your microphone not working? Maybe not, because you've got some comments here about electrons do not travel inside the wire. They are always going sometimes one way, sometimes the other. So are you talking about like AC current? I mean, there's definitely situations where they do that. And certainly if you're sending a signal like our Ethernet, that is sending a pulse on a wire, a compression pulse, not really flowing. But if you have a DC battery connected to a light bulb, then definitely the electrons do travel, but surprisingly, they travel very slow, like on the order of 1 to 2 centimeters per second. So they move about this fast in an average light bulb. So really, really slow. And it's actually really hard to imagine how something moving that slow can cause a tungsten filament to glow to incandescence, right? It's like, how can something that slow create frictional forces of the sort that it causes metal to heat up to thousands of degrees in temperature? It's kind of hard to understand that. But it looks like we are at the end of our discussion today. So basically the topic of discussion was a little bit about COVID, but mostly about the emails that we were getting about displacement current. So we took a look at what displacement current is, how it's related to capacitors. And then we delved into that much more closely with Ian as to what these things like the div mean, about the magnetic field having a div of 0, and that the field lines always have to curve back on each other, versus the stationary charge where the div is infinity, or it just goes out. Although I'm still not quite certain what that has to do with the need for there to be a magnetic monopole. We got a little bit into the magnetic monopole. Bill gave us a demonstration of the refrigerator magnet. Now, personally, I still think that that's not a monopole, because you can see, if you put that sheet on one of these magnetic field detectors, you can see an alternating stripe of north-south, north-south, north-south. And I'm not exactly sure why when you flip it over, it's not magnetic. That's probably just a mechanical artifact of how they magnetized it, such that there's not enough field strength back there to do it. But it's clearly... it's not a monopole in my opinion, so, because you can detect the north-south stripes. There's definitely something there that's not monopole-ish. But once again, I'm not sure whether it matters. But mostly we were discussing the males, which were debating the actual mechanism by which radio waves are received upon antennas. So everyone agrees that what comes out is electric current. And the emails are saying that the electric current, according to Maxwell's laws, is being caused by the magnetic induction. So it's like, and like the electric part, I don't know what it does, but apparently you don't need that, since the electric field doesn't generate electric current, only magnetic induction goes. And then I was trying to represent, my alternate view of the world, which is that this has nothing to do with electric or magnetic fields at all. Actually, it doesn't have anything to do with charges, as Bob was trying to say, that Weber electrics Weber's equations might be able to explain this, but I'm saying that there is just some medium in there. It doesn't have to have anything to do with charge. It could be neutrinos or neutrons. There's something that has no charge. It could be little green men, for as far as I know. But they mechanically hit against the receiving antenna, mechanically pushing electrons into the metal, thereby increasing the voltage, right? So that has nothing to do with electric field or magnetic field. You know, in my email, I said you could sit there and hit a rod with a hammer, and you would probably see a same kind of varying electric current coming out of it. Probably. I didn't try it, but it's probably true. And that means that there's that breaks the connection between induction causing this electric current through EMF and being radio waves. So, but that was kind of the topic. Mostly, once again, we've been exploring the nature of radio waves, since that, and displacement currents. There were like literally hundreds of messages, and they've only just like gotten to the very tip of this iceberg. I'll probably have to spend another hour or two plowing through them and maybe making some replies. But that will be this topic. So thanks for everyone showing up, and thanks for showing up right at 7 a.m. Pacific time, which is when we start, or 10 o'clock Eastern, or in other time zones. Thanks for coming, whether it be the evening or afternoon for you. And thanks to everyone for showing up on the live stream. We appreciate you showing up, and keep the questions coming during the discussion. Like I said, this is an open discussion, and we're just here to discuss whatever's on your mind. And I'm just here to trying to keep on stirring the pot. All right. So thanks a lot, guys.